We present InterDiff, generating 3D human-object interactions with physics-informed diffusion. Our task is defined as, when presented with past sequences of human-object interactions illustrated by gray meshes, we want to predict vibrant future sequences, shown in colored meshes. In existing methods used to predict human-object interactions, a skeletal representation is often employed. However, this fails to truly capture the nuanced, real-world contact between the skin and objects. While the field of interaction synthesis has evolved to incorporate skin meshes, much of the existing research remains constrained. Typically, it centers around actions such as approaching and grasping static objects or sitting on a static chair. State-of-the-art techniques leverage control policies within physics simulators to produce human-object interactions. Yet, these policies still only address a predefined and limited set of actions. Our approach diverges from this norm. We intend to address real-world complexities, such as the vast variability in objects and actions, and is representative of our daily interactions. Our methodology stems from a simple yet important observation. While overall human-object interactions might appear complex, the motion of an object relative to its contact point often exhibits a straightforward and predictable pattern. For the motion clips on the behave dataset shown here, the relative motion on the right might revolve around a steady axis, or remain almost static. Drawing inspiration from this observation, the key is to integrate coordinate transformations into our generative model that synthesizes the interactions. Specifically, we introduce an interaction correction step, designed to adjust the object's motion based on the contact reference. Here's how it works. Given a human-object interaction sequence, derived from any generative model, which might contain anomalies such as contact penetration. However, coarse contact information can be inferred from geometric cues, though the interaction sequence might not be perfect. And a reference system can be determined using this contact information. With this reference in place, we train a network to correct the relative object motion and promote the interaction plausibility. The resulting predicted motion is then reprocessed via a reverse coordinate transformation, preparing it for the next phase. In our approach, we embed the interaction correction step into every iteration of interaction diffusion. Here, interaction diffusion is a generator built upon the denoising diffusion probabilistic model. We employ a transformer-based encoder-decoder architecture for the parametrized reverse diffusion, which is tailored to map past motions and object geometry to their denoised future interaction. Here's a step-by-step breakdown of our process. First, during each cycle, we derive a denoised interaction sequence from the reverse diffusion process. Then, a correction scheduler evaluates the sequence to ascertain if any refinements are required. If corrections are deemed necessary, we use the interaction predictor to correct the object motion with the contact reference inferred, and finally reintegrate the correction into the forward diffusion. Note that the diffusion and correction aren't intertwined during training. Instead, they merge seamlessly during inference, without fine-tuning. Here are the results. We compare our proposed method InterDiff with the baseline MDM on the behave dataset. InterDiff consistently outperforms in terms of both human and object accuracy, as well as interaction quality. Notably, compared to plain diffusion, our method excels by providing more enhancements over a broader sample size. Furthermore, we can observe that InterDiff's ability to predict precise object motions notably boosts the accuracy of human movement. Consistent with the quantitative results, we observe that our approach InterDiff yields more plausible interaction predictions. Implausible interactions are highlighted in the red dotted box. Comparing with the ground truth motion. Our method produces smoother interaction sequences, despite being trained on noisy mocap data. We also conducted an ablation study that shows the efficacy of the coordinate transformation. In the absence of reference system transformation, the object motion integrated into the diffusion fails to align and catch up with the contact's motion. This misalignment leads to notable artifacts, particularly in long-term autoregressive generation. In summary, we introduce InterDiff for predicting 3D human-object interactions. This approach addresses real-world complexities, factoring in dynamic objects of diverse shapes, comprehensive body movements, and ensuring interactions that are sound. The InterDiff framework, enhanced with physics priors, has proven effective in this novel task, showcasing its immense potential for practical applications. As we look to the future, we're keen to expand our approach to more intricate environments. This includes scenarios with multiple dynamic objects, objects of increased complexity such as articulated and deformable entities, and interactions involving other humans. For more details, please visit our website. Thanks for watching.